Okay, welcome back, and we're continuing on with a different incline block problem this time. And the main difference from the last problem is this time we're going to be talking about friction and how it affects the acceleration of a block on an incline. So, in this problem, we're asked, does the block slide down the ramp? And if so, what is its acceleration? So, as we know from the previous video, let's just draw a free body diagram of the situation to analyze what effect friction plays. So this dot is going to represent the block, and so as we discussed before, we have a force of gravity, which is also called the weight, acting straight down. We have the normal force from the ramp onto the block, which is going to be, of course, perpendicular to the ramp. That's why it's called the normal force, because normal means perpendicular. And then we have the angle as before. So like we did in the previous problem, we're going to want to break down this force of gravity into its components. So we have the perpendicular component, which is going to be mg, this is going to be, so force of gravity, it's going to be mg cosine theta. And we have this parallel component over here. I'll just draw that over here. Fg parallel is going to be mg sine theta. And this holds for any inclined block problem. So just, if you forget how to derive these, just remember that this theta is equal to this angle over here. And you can get to those two expressions quite simply. So this time though, we have to deal with friction. And the frictional force, I put the equation over here, and I didn't think it warranted a separate video, so I would like to include it in a inclined block problem so you understand it in context. So the frictional force is a force that opposes motion. Since the block, if it were to slide, it would slide downward. The frictional force is going to oppose that motion of that parallel gravitational component, and it's going to be pointing this way. So this is the force of friction. Now, what we have to consider when we're dealing with the frictional force is something called, this is the Greek letter mu, and it represents the coefficient of friction. So in this case, we have a coefficient of friction of 0.6. It doesn't have any units associated with it. And you multiply that by the normal force, which is, I forgot to label, force normal, and we determine the force of friction. So basically, in this problem, what we're trying to do is determine if this force of gravity parallel is greater than the force of friction. If the force of gravity parallel is greater than the force of friction, then it will accelerate. Then block will accelerate. However, if the force gravity parallel is less than or equal to the force of friction, it won't accelerate. No acceleration. So what we're going to have to do is determine these two values, compare them, and see even if the block will slide down the ramp. And if it does slide down the ramp, we'll have to go back and follow a similar approach as the previous inclined block problem. So now that we have the basic concepts covered, let's do some calculations. Okay, so basically we need to determine Fg parallel and the force of friction. So let's start with the thing that we're more comfortable with. So the force of gravity parallel is just going to be the mass times the gravitational force times the sine of theta. So it's going to be 25 kilograms multiplied by 9.8 meters per second squared. And then we're going to multiply that by the sine of 30 degrees. And this comes out to about 122.5 newtons. Now let's consider the force of friction. We're just going to use this simple formula over here, which is mu times force, normal force. So let's see, we have our mu, which is 0.6. Here, let me write this. Use force normal. All right, so we have our mu value, and we have our, and now we have to determine the normal force. So what we're gonna have to do is write a force statement. So since these two forces, since the block doesn't move on this plane, it doesn't, the block isn't pushed up by the ramp, or the ramp isn't pushed down by the block, we can write this statement over here that the sum of the forces in the perpendicular plane, they're equal to 0. So we have force normal minus the force of gravity perpendicular is equal to 0, and then we get that force normal is equal to the force of gravity perpendicular. And by this, we can determine that the normal force is equal to the this right here, and we can sub in F here. So I should probably keep it in variable form. So force of friction is equal to mu times the normal force. Let's do a simple algebraic substitution. And now mu times the force of gravity perpendicular. Now this is equal to mg cosine theta. And now we can plug in our values of 0.6, 25 kilograms, 9.8 meters per second squared, and cosine 30 degrees. Oops. And when you do plug it in your calculator, this comes out to about like 127.3 newtons. Now for the final comparison, we have the force of friction and the force of gravity. So like I said before, 127.3 newtons is greater than 122.5 newtons. Therefore, the block will not slide. And this is pretty cool result, I think, because usually we would just assume that the block would slide down, but since this mu value, this coefficient of static friction is so high, it's 0.6, and the maximum value can be is 1, that explains why the block doesn't slide. And yeah, that's how you do one of these incline block problems. And
alright guys, so one more thing that we forgot to cover with the incline block problem, which is pretty important to understanding how it works, has to do with the force of friction. So if you look at the answer we got, we basically determined that the force of friction is 127 newtons roughly, while the force due to gravity down the ramp is 122 newtons. So we basically said that because of this, because the force of friction is greater, the block will not slide down the ramp. However, if you look closely at our answer, you might also wonder, if the force of friction is greater, how come the block isn't sliding up the ramp, right? Because we now have a net force up the ramp. And this leads us to an important topic on friction. So when we solve for friction with this equation, when we use the coefficient of static friction and we multiply it by the normal force, we are getting a maximum force of friction which may be supplied to oppose the motion. However, this is not the instantaneous force of friction. So let's take this whiteboard right now. So the whiteboard right now is not moving, meaning in a horizontal direction, like if I was going to push it this way, there's no force of friction being applied right now because there's no force that's opposing the motion. The whiteboard doesn't have any motion. So let's just say the force of friction for the whiteboard, if we just theoretically calculated it with mu and the normal force, let's just say it's 60 newtons for this whiteboard. That's the maximum force of friction which may be supplied by the whiteboard, but it's not the force of friction that's being supplied right now, because right now we don't have any motion for friction to oppose. So say I push on the whiteboard now, well, it's not sliding. Now that's because friction is matching the force that I'm applying on the whiteboard. If we take our theoretical force of friction of 60 newtons, I might only be applying a 30 Newton force on the whiteboard. And because that's less than the maximum force of friction, the whiteboard will oppose my motion with a 30 Newton force of friction. However, if the whiteboard starts to slide, that indicates that I've surpassed the maximum force of friction, which is 60 newtons. So in the case of this block problem, 127 newtons for the force of friction indicates that that is the maximum force of friction. Now, because the maximum force of friction is greater than the force due to gravity, it means that the friction will match the gravitational force, therefore the block won't move. If we had a force due to gravity that was greater than the force of friction, it would mean that friction would only oppose the block's motion up to 127.3 newtons. And then after that, it would not oppose the motion and the block would ultimately slide down.